Hi everyone, I am Dr. Askar Misbahi. I'm a clinical physicist specializing in radiation oncology. I'm passionate about helping radiotherapy technologists and students understand the physics behind the linear accelerators and radiotherapy, medical imaging, X-ray, CT, and other imaging systems used in medicine. In this talk, we will explore how electron beams are used in radiotherapy to treat cancer. You will see how electrons are accelerated inside the linear accelerator, as we say it, Linac in this talk. And also we will check main components working together to produce a clinical electron beam. Whether you are a medical physicist, radiation therapy technologist, student, this talk will give you a clear view of the science behind the technology. Now let's take a look at this Linac figure. It is the figure we can see in all hospitals we are working or we are going to work. A linear accelerator is a device that accelerates electrons to high energies in a straight path using radio frequency waves and produces electron or photon beams for radiation therapy. So this machine produces two sort of beams, electron beams or photon beams. But the main thing that happens inside the waveguide is acceleration of the electrons. So the main of radiation beams, electron beams. From outside, a linac consists of a treatment couch, treatment head, the rotating gantry, and supporting stand. You can see clearly on this figure. Actually, the patient lies on the treatment couch while the gantry rotates around them, allowing radiation to be delivered from multiple angles. This design helps deliver a high dose to the tumor while minimizing dose to nearby healthy tissues. As we know, it is the main aim of the radiation therapy. The gantry is a mechanically heavy structure mainly because the treatment head contains a lot of metal components and extensive radiation shielding. In addition, modern linacs are not just treatment machines, they are also advanced image-guided radiotherapy systems. It means that they can take images before patient treatment to help the setup of the patient or during the treatment. One type of the imaging which is older than the other is megavoltage portal imaging, which uses treatment beam itself together with a electronic portal imaging device. I have shown this on the figure as a portal imager. It is called EPID to verify treatment field and patient positioning. So it uses the X-ray beams coming out of the patient and can take those X-rays and build the image based on the exiting radiations from the patient. Also, Linacs are equipped with on-board kilovoltage imaging system. As I have shown on the figure, you can see X-ray source and KV imager planner. A KV X-ray source and a flat panel detector are mounted perpendicular to the treatment beam. It can be seen clearly. Enabling planar imaging, it means the image like the radiography, as well as a cone beam X-ray CT. It can create CT images using a cone beam system. It is a little bit different with our conventional CT, which we are using in the imaging centers. This provides three-dimensional images of the patient immediately before or even during the treatment. The main thing in the electron acceleration happens inside the treatment machine can be seen on this figure. If we look at the inside the Linac and see how all these parts work together to deliver a precise radiation therapy, we can see multiple or several components working together, and it is not really easy to explain all of these components. I have tried to briefly explain some of them. They are very important for electron beam production, and for the rest of that you can refer to the textbooks and engineering books about the linear accelerator. So at the main controlling part of the system is the control unit. Control unit is an electronic system that controls all the thing happens inside the Linac. You can think of this as the brain of the Linac. It controls energy, every operation, checks safety systems, and makes sure the treatment plan is delivered exactly as prescribed. This is very important when we prescribe those based on the monitor unit and amount of the radiation. It should start and stop and deliver the same amount of the radiation to the patient, and it is done by this part, control unit. The other important part is pulse modulator, which sends carefully timed and high voltage pulses to electron gun. And electron gun produces a narrow beam of electrons. And this electron beam is the starting point of all treatments. Next, the electron enters the accelerating waveguide. It is the other important component of the Linac. So if we start from the pulse modulator sends signals, electrical pulses to the electron gun, then electron gun produces the primary electron beams, and these electron beams are sent to accelerating waveguide. This part is the main part where the low energy electrons in the range of kilo electron volt are accelerated up to 20 million electron volt. Here they gain energy using microwave radio frequency power. In other slide I will explain how the acceleration happens inside accelerator waveguide by the radio frequency waves. It is a very important concept. We should talk about it. The waveguide is made of metallic structures such as a copper and highly evacuated using special pumps called ion pumps. So acceleration of the electrons inside the waveguide happens inside the air-free and in a vacuum which is provided by the ion pumps, and this pumps should work all days as far as we want to have the very stable situation for electron acceleration. In high energy linacs, electrons must be redirected to the patient. What it means that the electrons coming out of the accelerating section cannot hit the patients, and they should be redirected. And if you look at the figure here, you can see that we have bending magnet just above the treatment head, and it is very close to treatment head, which is responsible to redirecting the primary electron beams toward the patient. And between the bending magnet and the patient we have treatment head. Finally, the electrons coming from the bending magnet reaches the treatment head and get collimated and shaped to be delivered to the patient. Among the all components, the electron gun is the component responsible for electron production, so we will explain a little bit about it. It is the component that actually produces the electrons that will later become the treatment beam. So it is important in the whole chain of the electron production. Normally it operates using short high voltage pulses from the pulse modulator, which helps release the electrons at right time and with right energy. As you can see in the figure, we have filament which is generate which is resourced by the electrons coming from the pulse modulator, and using the thermionic emission it creates and produces the electrons, and the voltage pulse of around 10 kilovolt is applied, and electrons have the energy of around 10 kilo electron volt, and you end up with the pulse electron beams because the electrical pulse coming from the modulator, it is pulse, it is not continuous, producing instantaneous electron beam current on the order of milliampere. So the electrons produced in a 10 kilovolt and in the order of milliampere. It is not a big electronic beam. And the other thing is that, so when we have the electron source, electron gone, and the electrons are sent inside the waveguide, at the same time we should have the radio frequency wave inside our accelerating waveguide. So we need a source of radio frequency waves at the same time. By injecting the radio frequency wave and electrons at the same time simultaneously inside the waveguide, we can accelerate the electrons. Now we will talk about the sources of RF waves in a Linac. It has been shown in the figure. As you can see, I've tried to show you the magnetron cross section. It can uh, but we have another sources of the RF waves. It is called klystron. In this figure I have tried to talk about the magnetron, not klystron. Magnetron, which is basically the heart of microwave power in many linear accelerators such as Electra. The magnetron is actually a radio frequency oscillator. It takes energy from electrons and convert it into microwave waves using a resonant structure and a strong magnetic field. If you look at the picture, you can see that in the figure in the middle of the slide. It is a cross-sectional view. We have copper block which has some cavities inside, very symmetric cavities, and we have cathode, which is the source of electrons. So the thing is that radio frequency waves are produced from electrons. So in the magnetron also we have electrons, and these electrons are the source of radio frequency waves. Inside the magnetron, a heated cylindrical cathode emits electrons when negative high voltage pulses are applied, normally around 50 kilovolt and lasting up to a few milliseconds. It means the duration of the the pulses, electric pulses, around the milliseconds. The electrons are then drawn toward the radially symmetric anodes. It means that cavities and the copper block there. And as you can see in the figure on the right, we have a magnetic field which is applied along the cathode axis. I have shown these magnets by N and S, which shows the north and south pole of the magnet. And this field forces the electrons to follow curved paths instead of moving straight across. As a result, you end up with a rotating cloud of electrons. This rotating electron cloud transfers energy to the cavity oscillations, and the radio frequency power is generated from these electron beam clouds inside the resonant cavities. Finally, RF waves produced inside the cavity are extracted and sent to the accelerating waveguide. Now, when we have the electron source and radio wave power at the same time, they are injected inside the waveguide. And in this figure here, I have shown the waveguide of I think the variant Linac, which is the standing type of the waveguide. We have two types of the uh, acceleration waveguides. We have traveling and standing. It is the standing type. Waveguides, as we have the cross section of that, are evacuated metallic structures, as you can see in the figure. Structurally, the waveguide is based on the cylindrical tube with a series of discs or irises placed at equal distances along its length. So we have cavities and septums that separates the cavities, but there is a hole inside the septums or valves, as you can see in the figure, which connects the cavities together. We can say it irises here. It is very similar to iris in our eye. These irises form resonant cavities that shape the electric field used for acceleration. The electrons are accelerated in the accelerating waveguide by means of energy transfer from high power RF fields, which are set up in the cavities and are produced by the magnetron. In this figure that we have shown, it is a standing wave structure, and actually this design is very effective in producing and accelerating high energy electron beams. In this structure, both ends of the waveguide are closed with conducting disks. This causes the microwave power to be reflected back and forth. So a standing wave build up inside the structure rather than traveling in one direction. In this slide, I have tried to show you simply that how the electrons are affected by the RF waves, and we have one electron in this figure, but we have a bunch of electrons, and I have shown just one radio frequency wave, and it is very similar to traveling one, not the standing one, but it is the simple way to understand how the radio frequency wave can affect the electrons and push it forward and give its energy to electrons. Electrons are accelerated by radio frequency waves. It doesn't matter that it is standing or traveling. The main point is that the wave creates an oscillating electric field along the axis. So in this figure you can see that we have electric field, but electric field is oscillating. It means that it is not continuous electric field. It means that the negative and positive side of the electric field changes in time. It is alternate electric field. When electrons enters the waveguide, they experience a force from the electric field. So radio frequency wave produce electric field, and this electric field can force the electrons to move forward. If they are in phase with the accelerating portion of the wave, they gain energy and speed, and this process repeats over many cycles continuously from one cavity to other cavity and accelerating the electrons. It is very similar to a surfer riding on a wave in the ocean. So in this slide I have tried to propose a question which could be helpful to understand the concepts. What is the main function of the waveguide in a linear accelerator? To produce high energy photon directly, to guide and accelerate electrons using microwave energy, to scatter the electron beam uniformly, to generate the magnetic field for beam bending, and as we have talked about it, it is the second one, to guide and accelerate electrons using microwave energy. In here, I tried to talk about the treatment head, which is another important section that we should mention here in our talk. In this picture, you can see the electron and how the electrons coming from the bending magnet and are collimated or hit by several other components. It shows the pathway of the electron through the treatment head. From upper side of the figure, we can see that pencil beam exits the bending magnet and passes through the primary collimator. It then strikes the scattering foil, which is very important part of the treatment head, where the beam is flattened and spread out. And in this figure you can see that we have two foils here, first foil and second foil. Both of these foils are a part of the scattering foil system. Finally, the electron applicator, which is just below the secondary collimator. And then we will have at the end of the applicator we will have the custom cutout which precisely collimates and shapes the electron beam to exact treatment field size required for every patient. When we talk about the scattering foil, it is very interesting to see how it is in the reality, because when you draw something about the scattering foil, it is not really realistic, and I had a chance to take this picture from a real Linac. It is very small, and you can see that scattering foil has two components, first foil and second foil, and the responsibility of this part is to spread out the electron beams, because our electron beam is pencil beam, very narrow beam, and we should treat the patient with field sizes up to 25 by 25 centimeters. So we have to put something in front of the narrow beam and spread out it and make it uniform at the same time. So the first foil widens the beam by multiple scattering, and you can see it is very thin layer of the aluminum or other low low density metals. And the second one is works works just to make the beam uniform in the cross section. The electron beams reaches the patient's surface should be uniform, very uniform. The last part that we should know about the electron beam collimation is the electron cutout. In real treatment, we have several field sizes, and every patient has its own field size. So how we can make it in a reality, because we have around 4 or 5 field sizes can be produced by the electron applicator. So the solution is that we should make electron cutout for every patient and shape the electron for every patient based on the spread of the tumor region on the skin. So the electron cutout is located at the end of applicator, as you can see here. I have shown you, and it is the last part that reshape the electron beam for the treatment of the patient. I have very interesting questions always comes into my mind, and maybe some of the students or colleagues come across with this question. Why not we, why patients don't feel any electric shock in radiotherapy? So it could be explained this way, that the main reason is that electron radiotherapy is not an electric current. An electric shock happens when the electrons continuously flow through the body from one point to other, like from a wire to the ground. That does not happen in radiotherapy. In electron therapy, the electrons arrive at high energy beam, not as a following current. They enter the skin, travel a short distance, lose their energy, and then stop inside the tissue. And they don't pass through the body or exit on the other side. So because of that, nobody feels anything. The last question is, in electron beam mode, which component is used to broaden the narrow electron beam for clinical treatment? Photon target, flattening filter, scattering foil, bending magnet. So we know that the answer is scattering foil. It is the last slide I have prepared for this talk. This concludes our presentation. Thank you for watching.